So we're at the last part of today. It's been a really wonderful day, really wonderful talks, and I'm looking forward to the next two. And the first one is being given by Jim Lynch from Woods Hole Oceanographic Institution, and he's going to go into shallow water.
Yeah, going where nobody else has gone today. You can tell this is the serious part of the program by some of my slides here, but I've in different parts of my career, I've done deep water, shallow water, then back to shallow water and deep water. But anyway, I've been all over the map, but the past 20 years or so, I've been pretty much into shallow water acoustics, or 25. And he's my mascot over there. And the little poem there is called "The Grook" by a Danish poet, Pete Hein, who has some wonderful little tiny poems that he wrote during World War II as part of the resistance. Again, this is here in honor of Walter, and I haven't been a close collaborator of Walter's for many, many years, so but for at least a couple of years we went out on the Greenland Sea project, and I went out to sea with Walter, and I learned a number of really good lessons from Walter when I was out on that project. When Bob Spindell left Woods Hole, he said, "Jim, do you want to take over as PI on the Greenland Sea project?" So it took me a millisecond to say yes, and that's kind of how I came by Walter and Peter in the group a little bit more strongly. So, at any rate, see, here's some of the lessons I learned. And you know, Walter's one of our great scientists, but I learned also great scientists can be very human. When I was just a young scientist, about 38, and I asked him how his flight was from Scripps to Bergen, and I got a very colorful description from Walter of what the flight was like. So I figured, okay, check the box, he's human. And then the second lesson I learned was Walter was looking for somebody to take a little hike around the hills of Bergen. And I figured, oh, well, this poor 71-year-old man, I'll try and take it easy on him. And of course, it was a complete inversion. I barely survived the walk. Walter was quite happy. A third thing when we're in Bergen is that Walter gave a talk, and I don't know if he remembers it, but it was on like 10 or 12 crazy ideas from physics that might be useful in oceanography, and I forget the exact title. I don't think any of them turned out to be useful, but I thought it was wonderful that Walter would just cast the net that wide to find all, interesting things that might work. And then, kind of Walter's enthusiasm for science is a big part of things we all know. Walter was just crazy enthusiastic about every piece of the cruise. After a career of years and years, he would look at the XBTs, and whereas I'd go out and I'd see this little squiggly line, Walter would come up with this huge story about exactly what's going on in the ocean. And at first I thought he was just making this stuff up, but it turns out it was actually correct. So, and then kind of thinking big again. This is one of Walter's traits. He's not afraid to look at big issues. And also, he's not afraid to assault the sponsors' piggy banks for pretty much every cent that they can manage. And I actually learned that from Walter, not to be too shy. And so when we did a big experiment called the Shallow Water 06 experiment that I was one of the PIs on, we learned a lot from his teaching, and we almost took ONR for broke that year. Not quite, but we tried. And then, again, keep at it. I think Walter, at 71, he was like a 21-year-old, and I think at 100, not a whole bunch has changed. So Walter's enthusiasm just keeps going. So those are my little lessons, and I thought I'd pass those on that I learned as a young scientist. Now, if anybody's ever seen September Morn, it looks exactly like that picture, only reversed. So that's kind of a mirror image, and dipping her toes in shallow water. And my topics that I'm going to talk about are 3D acoustics, which you can pretty much figure would work in shallow water, and also climate change, which is, you wouldn't say, what the heck does that have to do with anything in shallow water? So I'll start out pretty much, and most of it will be on 3D effects, which turnout, you can see these due to surface waves, you can see them due to the water column, you can see it due to variable bathymetry or bottom structures like ripples. And all these things have some very nice 3D effects. And of course, climate change is just natural cycles, so we all know that. Notice, by the way, that little emoji is a wink, so. So the oceanographic, I kind of specialized in looking what the effects of the ocean were in shallow water. Having been exposed to Walter and Peter in the group here, I got interested in the oceanography part of it. And so I kind of concentrated on that. One of my colleagues from Woods Hole, George Frisk, concentrated on the bottom, and we would just fight endlessly about which part was more important. Neither one of us was right, so they're both important. And we're looking at things like the coastal shelf break fronts, which down by New England, New Jersey, where we did a lot of our work, are important features. Eddies and intrusions. One of our big cottage industries was really internal waves, and especially nonlinear internal waves. And the interest there is that these nonlinear internal waves are very strong features, they're very compact, and things like mode coupling or 3D effects are very much affected by those short, brief features. And then one of the things more lately we've been working on is oceanography in slopes and canyons, so there's lots of good things, and how those affect acoustics. So start with internal waves. This is just a satellite picture from one of our early experiments called SWARM in 1995, Shallow Water Acoustics Random Media. And you can see Poseidon broadcasting groups of internal waves about 20 kilometers apart each tidal cycle, each M2 tidal cycle. And they're all heading towards New Jersey, and New Jersey seems to have survived it pretty well through the years, but Poseidon keeps throwing these at New Jersey. But the other little piece that you see right here is actually a mooring track going from a source over here to some receivers. There are actually 2 receivers down in this region. And we're interested, at least in this experiment in the beginning, is what is the effect of the oceanography on transmissions going across shelf. So we were doing fluctuation statistics for things going across shelf, and that was a lot of fun. But those things going across shelf, if you look at them underneath the water, this is actually a model called the donoidal model of an internal wave train or a solid bore. And it looks like this, and you see this little picket fence of waves here first, and then it kind of dies off and back. This is the original tidal cycle. It relaxes back to it later. But the features of interest are these guys here, because these are the strong scatterers that we had to deal with, and we're interested in seeing what they did. And there's two kind of geometries we're interested in. One is if we go, again, across shelf, just like I showed in the previous picture, and the other is we go along shelf, which is basically going in between the picket waves, going into the board here, basically. And this is a picture of real data, and you can tell it looks ratty, so that this is obviously real data. But you can see these little picket fence guys here. And the internal tides are not quite as regular as our little pictures are, but these features are very much the same as far as the physical results you get out of them. Now, the interest in this actually started from what the Chinese did in about the 1980s. They did some transmissions in the Yellow Sea, and there's a Zhizhang Zhou, a lot of people here in this room know very well, and his collaborators, Peter Rogers and others, worked in the Yellow Sea. And they looked at sources which were creating low acoustic normal modes, which hang near the bottom. And these low modes would hit these internal wave trains, and they would scatter, and they'd scatter into the higher modes. This is a mode coupling effect. And these higher modes are lossy. They interact with the bottom more, so they lose more energy very quickly. And he would see 20, 40 dB losses and stuff. So these things basically could kill a transmission from something near the bottom. Whereas in another case, if you put the source up near the top here, and this is just a sound speed profile here, it would create the high modes as well, not so much the low modes. And these high modes would hit these waves here, and they'd scatter into low modes. And this is actually what happens if you look at shipping, which excites things near the surface of the water, or surface waves. It creates these high modes, And you'll see the distant shipping or distant storms and stuff just from the acoustic energy in a low mode, so it makes it propagate further. So there's some interesting physical effects there, and this is the cross-shelf geometry. So this is going across the waves, and that's what we first started to look at. Now, in every group, there's a contrarian, and there's one sitting in the room, his name's Mohsen Beatty. There he is in the back. And whereas everybody else went across shelf, Mohsen decided, I'm going to go along shelf. So, he didn't want to deal with the rest of us. And what came of Mohsen's little contrarian activity there was that if you put the sound source in between that little picket fence there and into the board, you would actually see the sound energy focused, so that the sound energy would propagate in between these things. These are like barriers. It's like a little potential well. It sits in here, and it propagates quite nicely through here. And as these waves go across, as the internal waves propagate across the shelf and stuff, they go from being ducted, like over here. Whoops, I guess this thing's kind of dying on me. That's okay. The top part of it there. And they'll go to right on the peak of one of these waves, and it creates an anti-duct. And that just spreads the energy out. You see the intensity lost very quickly. So that's kind of a nice little effect. And I'll show you in a second. What's cute about that is you could make a very simple model of that. Shallow water has some nice simplicities to it, as well as complications. And if you take a look, normally a source in shallow water would see cylindrical spreading. It's hitting the top and the bottom. It spreads like a cylinder. However, when you put these two waves here in between the two waves, it creates a duct. And it's like a school hallway because both the top and the bottom are reflective and the sides are reflective. So basically it's containing the sound, and the only losses you really get are the losses to the bottom or maybe surface scattering. But so all of a sudden, if you just take the area, the ratio of the areas of what you would have had with spreading versus the ducting, you can calculate versus range what the dB difference would be. And you see these things will give big changes in the dB level of the signal you see. So that's it's anywhere 4, 5, 6, even 7 and 8 in big cases. And when we put out the instruments and measured it, and these are Mohsen's measurements, we actually did see this. And you see these big stripes coming across. This is the internal waves as it focuses and defocuses. So this is a very nice three-dimensional effect because it's bending out a plane and it's focusing. So that was kind of the simplest effect we saw there. And if you notice, they're kind of right all the way through the water column, and that's because really the effect is on the higher modes, which do extend through the whole water column. So that's why you actually see that thing covering the whole water column. Now, as I mentioned, we were encouraged by some of these initial expenses to try and see if we could break ONR's budget. And so we decided to do SW06, and this is in the grand tradition of Walter's big experiments and stuff like that. So the idea was basically to raise mean sea level by putting in as many moorings as we could. And we had 64 moorings, I think, we put out. And we actually got 63 of them back with data. And it was amazing. The one mooring we actually didn't get back exploded. And we were able to use that as a broadband source. Yeah, wonderful broadband source. And in fact, I think that the distant monitoring stations did actually give us our mooring location from that. So it was just a wonderful demonstration. But we had about, in the course of 2 months, we had 4 or 5 ships. We had a long shelf and a cross shelf configuration here. And what we did, we weren't really trying to do the acoustics to get the oceanography. Instead, what we did was we conscripted all the coastal oceanographers we could find, said, you put your gear out the same time we put our gear out, and that way we could see what the oceanography and acoustics are doing at the same time, and that made eminent good sense, because they're better at the oceanography than I am, and they took some darn nice measurements. So that's just a little look at stuff we did there. Now, in order to give a little bit of a bow towards tomography, I should mention that the original sources from the tomography demonstration experiment, you could see a 224 hertz line down here, or actually a broadband, but it looks this little line here. That's the original tomography demonstration sources that Bob left when he left Woods Hole. And then we had 400 hertz sources here, which were generously loaned to us by Carl Lynch. We'd used those in the Gulf Stream, and Carl gave us the go-ahead to use them in some of our shallow water work. So we do have some inheritance from tomography here, so I can say we have a little tomographic pedigree in shallow water. And then the other thing we did is we filled as much of the band we could up towards mid-frequency with any signal we could. Nowadays, we would be, shot hung or something else like that for putting that much sound in the water. But back in '06, this was a legitimate thing to do. As far as what we saw out there, the satellite images were very, very good, and giving you some basics here. And one of the things you see is that these internal waves, they're planar on a short scale. So you go to short enough scales, a couple kilometers, yeah, it looks nice and planar and stuff. Go to a little bit bigger scale, they're curved. And that's because these are actually waves being created by the tides coming in on the shelf and through canyons and the rest of it. And they do have some curvature. It's not a straight line, straight edge shelf or anything. So, and there's also currents in the rest that bend the waves. So there's a lot of things that actually distort the wave shape into curved waves. So we got kind of interested, okay, what happens with curved waves? And what we did is said, okay, let's just, well, the first thing we did, just do some numerical modeling. And so those little, I wish this thing had a little bit better battery life, but oh well. Those white lines that you see, if you look in the upper left box there, are internal waves. And we put a sound source in between them. And what you could see is that some of the sound energy is actually curving around and bending with the internal waves. Well, guess what? It's a light pipe. It's just like the little light pipes that you used to see after lava lamps went out. You could bend them and stuff, and the light still came through the far end. But it's a funky light pipe. It's not quite as not your standard issue. And if you look at the second one on mode 1 intensity, mode 1's not doing too well as far as ducting goes. In fact, it just wanders underneath the duct and goes its merry way. Whereas mode 2 in this little numerical example is following the ducting. And that's, again, because of something I said a few minutes ago, is that the low modes are concentrated near the bottom, whereas these internal waves are up near the surface. So the low modes just scoot right underneath it. They don't care. The high modes do see this and actually get trapped by the internal waves. And there's, if you take a look, this is a parabolic equation calculation down here, where we actually can see the evolution of the sound source as it goes along that black line up there. And you could see it right here, you could see a few modes interfering here. There's probably 3 modes in this particular example we have here, 3 or 4. And then as you go further along here, they die out, you just start to attenuate, and you actually see just mode 1 down towards the far end there. And then all of a sudden, you see mode 2. So in between those 2 dotted lines, all of a sudden you see the region where the duct is crossing there, and you see mode 2. So you absolutely see a very nice example of the ducting if you take a little cross-sectional piece. And one other thing I'd like to say, if those internal waves there are actually kind of a weak wave, they're a weak constraint. It's not a strong duct. You go up to about 5-6 degrees and it's over. So the critical angle is about 5 degrees. And actually that tends to be true of surface waves, bottom ducts, and the internal waves. They all, from the simulations we've done, have very small critical angles. So you have to hit these things at very close grazing incidents to actually see some effects like this. So there's interesting piece to that. This is another thing that I thought was kind of cute here is 3D sound propagation modeling, where you put the source now, instead of in the duct, you just put it above the duct here. And what you're seeing here on the top part of the graph is you're seeing the interference between the direct path and the reflected path off that thing there. It's a Lloyd's mirror. It's a horizontal Lloyd's mirror. In the ocean, we see that in the vertical when the sound goes either direct or reflects off the surface. In this one, it's just horizontal. So you can see the interference pattern there. Well, that's kind of cool. It's a numerical model. Well, this is even cooler. That's data. And the nice part about this is, like I said, mode 1, mode 2, mode 3, go underneath the internal waves out of our experiment. But if you take a look at mode 4, look at this. Here's a direct path between source and receiver. There's an internal wave coming towards it here, like my two arms are coming together. And as the wave gets close enough, all of a sudden you start hitting critical angle, the wave will reflect off it. And you'll get the biggest time difference between the direct and the reflected one. As the wave gets closer and closer, these things start to merge. And as the wave closes, as it closes totally here on the wave, you start to hit the antinode and it disappears. And that's what you see at the bottom. So this is a really nice physical example with mode filtered data of a horizontal Lloyd's mirror effect. And there's some of the physical effect, very simple effect, but it works. The physics works very pretty. One of the things we're still doing, and in fact, I think ONR still has some programs here looking at bottom ripples and how those affect sound, is that we've actually done, one of my students did a thesis where he looked at surface, internal, and bottom guiding of waves and stuff. And what's kind of fun is that the surface waves probably aren't the big actor here because the surface mix layer kind of pushes energy away, but the internal waves, we've just seen what they do. The bottom waves, the bottom ripples and stuff, and these do exist around the world, actually affect the low modes the most. And the one thing you know about shallow water is most of the energy winds up in the low modes usually. So in terms of energetics, if there's regions where there's type of bottom ripples around, that's actually going to be a dominant effect. Or if there's both internal waves and the bottom ripples, you'll see both having an effect. And there's also no law that says that the internal waves and the bottom ripples have to go the same direction. So there's the directional spectrum of all that. And so it's kind of, again, a cute little piece of physics. This is a numerical example. Note this is not spin art that my daughter did when she was young. There's of actually ducting of, this is bathymetry off San Francisco Bay. So we actually put in a sound source there. I forget what frequency it is even. I'd have to go back and look it up. But we published it in a conference proceedings. But you can actually see how the sound hits these ripples, and it does guide it, and you wind up with these nice little beams of things. So it's a very cute effect. And I feel bad with this audience not having one equation, so I put this here. This is actually one simple way you calculate 3D acoustics, which I think Rob Pinkel has used in physical oceanography, and the acousticians use for 3D acoustic theory. And it's called horizontal rays and vertical modes. And the idea for this is a very basic 3D calculation. You calculate the mode set at every XY point in the plane. You get the modal eigenvalues. You take the ratio of modal eigenvalues at one spot to the other. It's a relative index of refraction. You do ray tracing in the XY plane. You multiply the two solutions, you've got an acoustic field. Now, that's, in a sense, that's the nicest physics. You can actually see it. It's adiabatic mode theory, what's called adiabatic. The modes don't couple. But you could actually see very nice as a picture. Whereas if you go to more complicated calculations, like we're working a lot on 3D parabolic equations, you get wonderful answers. They're absolutely far more correct. They include mode coupling, all sorts of odds and ends. But you won't see physically what's going on. It's a wonderful black box. So this is kind of something we use to kind of check over just physically what's going on. Now, I mentioned, I got a few more minutes here, right? Yeah. I was going to do climate change. Well, not really, but we did do something. I went off on an experiment 2012 with Glenn Gaworkowitz from Woods Hole, and we were looking actually at fish scattering. We took a stroll down there. Glenn's called the Greek god of bad weather. We actually had 2 tropical storms in 3 weeks, we went down there and we were looking for cold water fish. We had a fish biologist from Rutgers, this guy Motz, who was, said, oh yeah, here's what we're going to see. We're going to see butterfish and all these cool water, fish and stuff. And we got down there, and first of all, Glenn was doing his scan fish and the rest of it, looking at the profiles. Well, it wasn't anything like the climatological profile, totally different. And the other thing we saw was, instead of cold water fish, we just got a whole heaping helping of warm water fish. And these are called blue runners, and they taste awful. But, but that was warm water fish. And I think the biologists know very well right now that species are migrating further and further north to get to cooler waters. The waters are changing as a function of latitude. And it's certainly an effect we're seeing in shallow water. And Glenn wrote some papers saying, look, that change we saw in the scanfish results also, it wasn't just moving across the front or some silly thing like that. It was actually very probably due to climate. So even in shallow water, you know, off the coast and stuff, we're seeing things, you know, that are climate. And I think this is in terms of Walter's work. You know, in 88 and 89, I had the pleasure of going out with him and Peter and the rest of the Scripps crew on the Greenland Sea Cruise. And we're looking at deep convection, which may or may not have been tied to climate change as part of the ocean conveyor. It just supplies deep water, which then supposedly wanders down south. This doesn't wander as much. The Greenland Sea is not a big important player, but it's wonderful physics. But so we looked at that in 88, 89. Well, it was still convecting and stuff, so okay, that was nice. We saw the deep convection. In 94, Walter did his ATOC project and mounting a major basin scale effort to catch a definitive glimpse of climate change. Let's see if this, you know, is it real? And in 94, people were still asking, you know, how real, how big is this? In 2012, we were in shallow water. We weren't in the least interested in looking for climate change, and it came looking for us. So, I mean, we're living in a world now that, you know, what Walter originally was looking for with very sophisticated efforts, basically, you know, you don't have to look very hard anymore. And that's, and then the other thing is the implications for shallow water acoustics. You know, as a result of the shallow water programs, we learned a lot about the physical oceanography and acoustics of the shallow water regions. And that collaboration between the oceanographers and the acousticians was wonderful because we were able to make a lot of sense of our data and share resources. And this knowledge in terms of defense, as far as I'm concerned, gets passed up the ladder, you know, to see if any of the stuff we saw is exploitable for the Navy, can be processed away, can it be safely ignored? What do you do with it? So we have this understanding of the processes, what do you do with this? And again, I'm lazy, so I mostly leave this to the Harrys and the Arts and the other people in the world to figure out the significance. You know, implications for climate, again, we all know this. This can really affect our coastal food chain, you know, if we're looking at coastal acoustics or coastal oceanography. You know, there's these fish, they migrate to a new place. It's not going to be the same habitat. They're not going to survive as well. And the same for other critters. You know, most of us live by the coasts. Most of humanity lives by coasts. And so we now see a little more severe storms by the coast, as we've seen last week. Some new unfriendly biota. There's lots of great whites now off of New England. And Glenn has been telling me on the side he sees some shifting and erosion of the shelf break front. So he's seeing some coastal effects. Now they tend to be a little more intermittent. Warmer cold pool waters, other effects. So people doing coastal oceanography now are looking pretty seriously. This will affect shallow water acoustics to some extent, but we're not the first order change in this. The first order change is in other things. And so let me just do a postscript on this. So, you know, thanking Walter for his leadership. And Walter really is the godfather. So I think in addition to his many other awards, I think Walter should get some sort of Godfather award. I'm not sure who gives that. I'm not sure if it's the mafia or whatever, but so that's my talk, and thank you.
Any comments or questions for Jim?
It's late in the afternoon.
Let's take him an offer he can't refuse.
I think Walter could refuse successfully if he wanted to, but yeah, we'll try. All right, thanks, Bob.
Thank you very much. Okay, so our last talk of today, Lora van Uffelen from University of Rhode Island, I think I'm looking forward to it because all these other talks have talked about past experiments, and Lora is going to make some prognostications about the next 100 years. So, looking forward.
All right, thank you. All right, thank you. Yeah, I don't have any really great old sea stories to talk about, so I'm going to look back a little bit, I'm going to look forward a little bit, and then I'm going to talk about an experiment that's actually going on right now. So I am a former graduate student of Peter Worcester. I'm having a little bit of deja vu / PTSD right now. The last time I gave a talk here was my PhD defense, and a lot of the same characters are in this audience. So, it's great to be back. So I'm really glad this morning that it was brought up that every event that Walter is part of has students involved, because I just wanted to reiterate that it was really wonderful to be able to look up to Walter when I was a student. And there's several things I admired about him, particularly his curiosity. It's really great to see somebody at that stage in their career, in that position, still asking questions and still really just wanting to know. Along with that is his humility, and I think those kind of go one in one together. He wasn't really in it for the glory. He just really wants to understand the ocean and understand acoustics, and I think that's really inspiring. And also, kind of where I want to go today is Walter's sense of adventure. And anyone who knows me knows that I really love going to sea. And so this is a quote from a 2015 New York Times article that was written about Walter. And it says, "Computers are a lot cheaper than boats and a lot more comfortable, and I'm a little worried about so many people doing computer experiments and losing their ability, the American leadership in measurements at sea." And so today I wanted to talk about measurements at sea. And so that's really the focus of this. So this is kind of a roadmap of where we're going. We're going to look back a little bit, look forward a little bit, and then the most of my talk at the end is going to be talking about what's happening right now up in the Arctic. So my title today is "The Sea Itself is Our Laboratory," and this is a line from a 1967 documentary called Waves Across the Pacific. And I'm just going to show a little clip of this today. I really love this documentary. If you haven't seen it, it's on YouTube. It's like 30 minutes, so look it up. And so I show this, I teach a course at University of Rhode Island called Introduction to Data Collection Systems. And I show this on the first day of my class for a couple of reasons. First of all, I think it imparts that sense of adventure in collecting data in the ocean. Second of all, it does a really good job of introducing spectral analysis. And third, which you'll see, it shows some really cool punch card technology. So, this is just a couple minutes long.
I was frightened by the idea of using such fancy digital equipment.
That was the best line, but I'm starting it from the beginning.
A group of scientists gathers at the La Jolla Laboratory of the Institute of Geophysics, University of California. Their discussion concerns the results of a unique experiment. They have been studying the passage of waves across the Pacific, identifying and following groups of waves all the way from their source in Antarctic storms northward to the coast of Alaska. Dr. Walter Munk, director of the laboratory, originated this study of energy, waves, and the sea. With his colleagues, he spent an entire summer tracking waves generated by the severe Antarctic storms.
The sea itself was our laboratory. Ocean swell, trains of waves moving across the sea, can come halfway around the world to deliver its power on the shore in the form of breakers. And here in the surf, the historic line of battle between land and sea, that power is immediately clear. Here the energy of the waves seems concentrated. In the past, our data was visually recorded by wiggly lines on paper. For this expedition, the data would be recorded on punch tape equipment for direct input into a computer. I was frightened by the idea of using such fancy digital equipment on remote islands far from repair facilities. but I agreed it was necessary because of the large volume of data we anticipated collecting. The speed of the modern computer would allow us to get some results while the stations were in operation, to play things by ear, and to improve our procedure in the field. We lived in a Samoan folly on the edge of the village. The house was built entirely of coconut palm, an ideal place to work on waves. The house was open on all sides. It afforded lots of comfort and no privacy. To operate our recording equipment, we had taken along our own generator. As at all the stations, we recorded for 3 hours twice each day, from 4 to 7 a.m. and from 4 to 7 p.m. Each day we punched out 10,000 data points to be digested by the computer at home. We hardly ever missed a measurement. The equipment worked admirably, and my initial apprehension soon vanished. Data taking became quite routine. My wife and some of the Samoans learned to operate the recording equipment. When at the end of the summer we finally returned to California, we had amassed 10 million data points documenting waves from 12 major storms. A person with a desk calculator would have taken 2,000 years to convert this data into a meaningful picture of what happened. With a high-speed computer, our analysis was finished within a week of the end of the expedition. In talking things over, we're pleased with how well these storms were documented by the experimental program. We are somewhat disappointed that the measured attenuation varied considerably from storm to storm, but this should be no surprise, for in nature, no two storms or no two waves are ever alike.
So I show this to my class, and they look up from their smartphones, you know, and just laugh at that line where Walter says, I was worried about taking this advanced technology to a remote island. So yeah, it's really, really great. And for fun, right after this, I took 1 million random data points on my my MacBook Pro laptop and clocked how long it took to do an FFT of that. It was 0.027 seconds. So that was in 1967. In that same year, Roger Revelle gave a talk at the IAPSO, for the IAPSO President's Lecture. That's the International Association of Physical Sciences of the Ocean. So it was in 1967. And then Walter gave a talk there in 1997. And so we're looking at, 20 years ago and 50 years ago here. And I have a quote from Walter quoting Roger Revelle. So this is me quoting Walter quoting Roger Revelle. Great periods of oceanography are determined by the development of new instrumental capabilities. And so there were a couple capabilities that were listed here, which I'm going to go through now, and then I'm going to talk a little bit about what are the new instrumental capabilities that will shape the next age. So this is again a quote from that talk. It said, computers were one of those great instrumental capabilities to investigate complex hydrodynamic models and to handle large quantities of data. And remember, at that time, this is what the kind of computers they were talking about. So we're still in this age. We're still at the point where computers are becoming more and more capable every day. We look at some of the ocean models that were brought up this morning, and this is really going to advance the state of art, continue to. Another thing that was listed was the development of free-floating and bottom-mounted instruments. And at the time, I believe he was referring to the swallow floats, but I just wanted to throw a picture up here of an Argo float right now, just to show how ubiquitous these instruments are in the ocean now. In that same talk, I think Walter famously called the first century of oceanography, that's the century since the Challenger expedition in the 1870s, called it the century of undersampling. And so we moved on from that, right? And so now we're trying to sample a little bit better. Back then, all the sampling was done on ships, and now we have all these instruments that can be out on their own or autonomous that can also sample the ocean. The many uses of underwater sound was also listed, and we've seen a lot of that today, right? So particularly acoustic tomography, which a lot of people have talked about today, but also we've heard about ecology and a lot of other internal waves and other applications of underwater sound as well. And then the last thing that was listed was the use of satellites to study the surface of the sea and for many other purposes. And this technology is also continuing to evolve. That was referring to the Topex Poseidon satellites, but we also use, obviously, GPS every day, right? We use it on our phones to find the nearest coffee shop or to find where we parked our car. But it's also used for localizing ocean instrumentation. And also we use iridium for communicating with ocean instrumentation. So this is going to continue to be a big part of ocean science and ocean acoustics. So looking forward, continuing with that talk, Walter says, if my or Roger's thesis is correct that advances in oceanography are dependent basically upon new kinds of instrumentation, the future of our science will be sterile unless we can continually find new things to observe and new ways to measure them. And so what I take from that is that we have to look outward, right? We have to look at other things that are going on in technology and in science to see how we can better sample the ocean, how we can better learn about that. And so I just listed, there's probably more, but I've just kind of listed 4 areas where I think technology is going to advance a lot in the coming years, and these will impact ocean acoustics and oceanography. And then also there's a number of areas where ocean acoustics can contribute to that. So first of all, there's big data, right? Data storage has come a long, long way. In 1979, you see a person is pushing a 250 megabyte hard drive. I grabbed this figure off the internet that shows 2005, that's 128 megabytes there, so it's about half of what that giant thing is now. In 2014, that megabyte became a gigabyte, and then 2 years later, that doubled to 256 gigabytes. And so this is also becoming much, much cheaper, which is having a big impact on ocean science. 30, 40 years ago, a gigabyte of data was $100,000 or more, and now a gigabyte of data is a few cents. So I just looked the other day, you can buy a 2 terabyte external disk for about $60. And so we have the ability to sample much, much more in the ocean. And so this is going to help us on our path away from the century of undersampling. Another thing that I think is going to shape ocean science is the way that we communicate and connectivity. And so this is one area where I think acoustics has a lot to offer, particularly underwater. With vehicles, they need to communicate with each other. And this is one way where acoustics can add to this through acoustic communications. The way of oceanography also is moving to be more connected. And I think the way that we do science, the way that we go to sea, is changing. And this figure here is from the NOAA website for the oceanexplorer.noaa.gov. And this is depicting the idea of telepresence. And telepresence has become kind of a buzzword over the past several years in ocean-going activities. So now what they do a lot of times, instead of a bunch of PhD scientists going out on a ship and deploying instruments, we're moving more and more towards a lot of trained technicians going out on ships and having a high data rate satellite connection. And so scientists on shore can watch this at home and direct the activities that are at sea. So this is done routinely now for a lot of ocean exploration activities, particularly with the ship Nautilus and the Oceanus Explorer, which is one of NOAA's ships. I'm at the University of Rhode Island, and there they have this inner space center, and so it's a huge screen in an auditorium, and they have this, they basically go in and they can look at images from an ROV on the seafloor, and they can tell the ROV pilot who's on the ship where to go, depending on where they want to sample. And so I think our world is becoming more and more connected, and this is going to shape the way that we do ocean science. What I really mostly want to talk about today, because this is the area that I have a little more experience in, it is underwater vehicles. I have a picture here of a glider, which I'll talk about a little bit more because I work with gliders, but also underwater vehicles. This is a Sentry. It's an AUV operated by Woods Hole Oceanographic. And I'm also glad that Kelly showed another AUV that was used this morning. AUVs, UUVs, these are becoming ubiquitous in ocean sampling. And they have varying capabilities. Sentry AUV is usually, it's kept right next to a ship, and it's usually sent out. It's got a sonar in it, a side scan, and it looks at the seafloor, and usually is done missions right before Alvin. So it's, you know, kind of plotting the course for Alvin. So it's right next to the ship, whereas a glider is more autonomous. They're put out there for months at a time on their own, and it's piloted from shore. But there's many other AUVs as well. And I'll show some of them here. This is just a figure that I grabbed from the website for a 2016 MIT workshop, but it shows all these different AUVs that are out there, right? These are becoming more and more ubiquitous. There's lots of different kinds. But this workshop was focused on robot localization and navigation, and that's going to be one of the key things that we're looking at in the future for this type of science, is how do you communicate with these vehicles, and how do you localize them, and how do you tell them where to go. And this is an area where acoustics has a lot to offer, and this is the point in my talk where I kind of want to move into some of the work that I've done, because I'm excited about this underwater vehicle navigation and localization. So I'm going to quick show a figure here. This is from a colleague of mine, Sarah Webster at the University of Washington. So she is interested in glider navigation as well. And so I'll show in a minute some glider localization work that I've done in the Philippine Sea. But we were both kind of trying to solve the same problem, but from very different viewpoints. Sarah was coming at it from a robotics and controls viewpoint, where she's implementing a Kalman filter, a 3-degree of freedom Kalman filter. I'll leave the details to the paper here, but what's shown in the figure here, taken from that paper, is about almost 2 weeks of data where a glider was going under the ice. And so a glider is underwater for about 6 hours typically, and then it comes up to the surface and it gets a GPS fix, and it reorients and then goes back down again. So it's checking in about every 6.5 hours or so. But if there's ice, it's not able to check in. And so what she did was set the glider under ice. And what's shown there is, in the purple, is shown a localization done using acoustic localization beacons at 900 hertz, and showing how the glider tracked with that, and then how the glider tracked without it. And you see these large corrections where the arrow is pointing, and that just shows that the acoustics are really needed to keep it on track, right? If the glider didn't have that, it would be going off, and every time it would come to the surface, it'd have a major correction to take care of. So this is the work that she was doing in the marginal ice zone. I'm just briefly going to talk about this acoustic localization that I did in the Philippine Sea. Peter showed a map earlier of the Philippine Sea where there were 6 acoustic tomography sources. So these are 250 hertz sources, and they were located up there. You can see T1, T2, T3, T4, and T5. T6 wasn't transmitting, so we didn't get receptors from that. So the direction that I went with it was I took these acoustic receptions, I matched them up with acoustic predictions, which is shown here. This is just the top 1,000 meters of acoustic time front. And so I kind of just shifted them back and forth to match up the peaks with the data collected on the glider, which is shown in black on the top there, and then took that offset, combined offsets from a number of different sources to get a localization for the glider. Not enough details, I know, but that's basically what was done. And what I found was that I could localize the gliders with errors of on the order of 80 meters RMS, which is an order of magnitude better than what is typically gotten with like a Rayfos transmission. So this was in the Philippine Sea, and so I approached Sarah and I said, how about we try to marry these two methods, right? So I'm using a pretty basic glider model. I was assuming the glider was traveling at a constant speed, whereas she used a more complex Kalman filter model. She used a very simple acoustic model where she assumed just a constant sound speed everywhere, and I used a more complicated acoustic method. And so we're trying to marry these two methods and see if we can get improvement. So I don't have any data to show you today, but we have an experiment going on right now. And so I wanted to tell you a little bit about that ongoing experiment. This is going on in the Arctic right now, right in the Canada Basin, which is located right there. This is a picture of the Healy. So last year at this time, Peter Worcester was out deploying acoustic moorings. I was also on that cruise and doing some glider work. So I'm just going to quick show a couple slides showing the canopé array. So the canopé is the Canada Basin Acoustic Propagation Experiment. He showed slides earlier showing the Philippine Sea Array, and this is kind of the same thing, but a little bit smaller and a little bit colder. It's farther north. So there are, again, T1, T2, T3, T4, T5, and T6 are all transceiver moorings. On each of these moorings, there is, an anchor at the bottom. There's a float that sits about 40 meters down, and then there's an acoustic source, which you see here. There's a sweat frequency source, transmits every 4 hours. So the sources transmit at 6-minute intervals. T1 transmits, 6 minutes later, T2 transmits, then T3, T4, T5, and T6, and so on. I also wanted to just give a little plug for the distributed vertical line array. So these are hydrophone module receivers, which are also a new technology in ocean acoustics that were developed at Peter's lab that were deployed first in the Philippine Sea. These things are pretty cool though. There's a centralized unit called a D-star, and this keeps very precise timing, and it tells the instruments when to record. So it can send a signal via inductive modem just up an ordinary mooring line. And so these instruments can just be clamped on a regular mooring line. Each one also has its own battery, and it has its own SD card for data storage. So if you end up losing one, you don't lose the entire array, which ends up being a big thing. Okay, so that's the overall canopé experiment. Now I want to move on to a kind of sub-experiment, not to be outdone with culinary acronyms. This one is called Cabbage. This is the Canada Basin Acoustic Glider Experiment. And so let me tell you just a little bit about what these gliders are. This is a sea glider. They're produced commercially by Kongsberg. And this one was outfitted with a Hui micromodem. So we're recording data on the micromodem and then also looking for source transmissions in real time. So the way the glider operates, they're very slow, but they operate really low power. So there's no propulsion or anything like that. They move up and down in the water column using what's called a buoyancy engine. And so basically all it does is it pumps oil in and out of that little purple balloon that you see on the back. So it's changing the density of the instrument relative to the water around it. So when it's at the surface, the antenna there is up in the air. It gets GPS. It sends back data, some data. It sends back temperature, salinity. It sends back log files. And then we also have the opportunity to give it commands. So we can tell it where we want it to go. We can change how it samples. And we also change parameters to make it fly more efficiently. So when it's ready to go down, that balloon deflates. The battery pack, which is the royal blue, shifts forward so that the glider dives down. It can go as deep as 1,000 meters, and then the opposite thing happens once it reaches the bottom or the apogee, and it comes back up again. So all the glider does is it keeps going up and down, up and down, up and down. And it can be out there for months at a time. So we did a pilot study last year at this very time. Those are just some pictures from the glider deployment. So when we were out deploying the moorings for canopé, we took out 2 gliders and deployed them at the beginning of the cruise, let them swim around for the couple weeks that we were out there, and then picked them up before heading back as just kind of a pilot study to make sure that everything was working correctly. This is where the gliders went. So we had 2 gliders. They're just known by their serial numbers. They probably need fancier names, but for now they're just Sea Glider 198 and Sea Glider 196. So they just traveled up between the transceivers, one going north and one going south. We picked them up at the end. These are some temperature data that were collected on the gliders, and this dark blue that you see, I don't have a, oh, do I? There. The battery's dead? Okay. The dark blue that you see is known as the acoustic duct. It's a cold area where we're trying to study how far we can transmit sound in that depth. It's also called the Beaufort lens, depending on who you talk to. So this is just temperature measurements collected on the gliders. I did a couple, this is acoustic data that were collected. And so this was in real time at the time, but we got about 385 hits. These are transmissions from the sources that were received on the gliders. One of them indicated in O's and one indicated in X's. So this was done last year, so we got the acoustic data back, and we just did a few comparisons with predictions. This is a PE prediction done with Peregrine, which was developed by the Oasis guys back there. I'm giving you a shout out. So really, at this point, we're just looking for whether the data collected on the glider makes sense, and it definitely does. You can see that we get a strong arrival at the finale here, and the PE shown at the top. On the bottom, this is the actual acoustic data that was collected on the glider. It's a little bit messier, but it makes sense. So we have a lot more work to do, but I'm just kind of showing the data that was collected now. So that was in the acoustic duct. We also made some measurements a little bit deeper than the duct. So this was at 423 meters depth. And in here, I've superimposed them. The arrival that was measured is shown in red, and the PE simulation is shown in blue. And again, you can see that they agree pretty well. All along here, we have a little bit more scattering in the actual acoustic data. Again, something that we're going to look into more, but pretty promising results. So that was all last year. We put 2 sea gliders out again. So they're actually out right now as we speak. So they were taken out earlier this month, first week of August, taken out to about where the shelf ends right there on the RV Ukpik, which is about a 50-foot research vessel operating out of Prudhoe Bay, Alaska. So the gliders are taken out there. They've been heading up towards the array, and this is where they were as of this morning. So they may be a little bit farther now, but they're out there collecting data. They check in with GPS at every surfacing. We were actually hoping to get some under ice navigation, but there's really no ice up there right now. So unfortunately, we won't be getting that. This I'm showing with a large grain of salt. We put some ADCPs on the gliders. But there's a lot to sort out before this data really means anything. Because the gliders are moving, we have to sort out how to remove the motion of the glider before using the ADCP data, but it is collecting ADCP data. What it sends back is also very decimated. So this figure I wanted to show, this is a screenshot from the website, and so I also took that this morning. It's getting close to 5 o'clock. The sources are also going to transmit again at 5 o'clock. So they're going on soon. But this is just a screenshot from the website. I mostly want to show Peter that all your sources are transmitting here. And so you see, if you go down, this is on the left column is the dive number, the source, and then the broadcast hour are what you see there. And so you see the most recent are on top. So you see T5, T4, T3, T1, broadcast at 12 GMT that were received. T5, T4, T3, T1 at 8 o'clock, T5, T4, T3, T1 at 4 o'clock, T5, T4, T3, T1 at 0, T5, T4, T3, T1 at 20, and then at 1600. So this is a day's worth of acoustic receptions that we're recording right now. Actually, I've recorded in the past like 24 hours. So that's kind of cool to see. I also plotted up all of them that we've collected over both gliders. So this is what we've collected as of yesterday. We didn't update this today. But you can see that the X's here are one of the sea gliders. The O's are the other one. You can kind of tell which is which, right? T3 is the green one, the one that was coming up here and is heading off that way. There's one of them that's getting closer to T1. So you can kind of track where the gliders are actually going based on the depths and ranges that they're collecting data. So that's really all I have today. I just wanted to say that I think going back to the original question of how is our ability going to see? How is that changing? And I think it definitely is changing. I hear all these stories about, the glory days of oceanography where, you could go out and you could throw TNT over the side, or, you could go live in a Tahitian hut for a summer. And I think those maybe are over. But I think there's a lot of exciting stuff to come. And I think a lot of this is going to involve autonomous instruments and vehicles. And I think these instruments need acoustics, and I think we can also learn a lot from acoustics using these vehicles. That's it.
Anybody have anything for Laura? I thought it was a great capstone talk at the end of the day. Looked ahead, and it's wonderful to see your enthusiasm.
Walter.
You started out by telling about the 8-hole tape
Yeah.
we used in waves across the Pacific. It itself was an enormous improvement over punch tape and the old IBM 650. And I wanted to tell you, when I started with Spectre, Canberra, the company here, gave me free time on the 2 a.m. to 6 a.m. shift. And I used to collect my punch cards at midnight and take off and come home at 6:30 a.m. with finished Spectre. and how much easier it is nowadays.
Well, that's great. Let's give all the speakers a round.
One last logistics, just to remind everyone, the symposium dinner is up at the IGPP Ravel Labs. It's up the hill. I'll be heading up in just a moment for those who want to treat me like the Pied Piper. You have a little bit of time. The bar will probably open up around 5:30-ish with dinner at 6 o'clock-ish or a bit thereafter. So you have time if you want to go to the hotel and collect a significant other or do other things. Those who want to go up can look out at the sun as it starts to head down toward the horizon. Well, thank you very much.